Hello. Today I would like to discuss the three-dimensional energy eigenvalue rigid rotator problem. This is the problem in the textbooks, but they are only 5 steps to end the to get final result. We need to solve this problem by step. So without wasting time, I would like to start this equation here. See, if you look at this equation carefully, first they are start with the Schrodinger equation, but it is in the form of a three-dimensional spherical polar coordinate. Then they are using the separation variable method to separate the uh, different type of functions. Here, theta is one function, y is another function, and finally they get the eigenvalue equation. The final equation they got actually. So here we need to solve this problem step by step to achieve this result. Okay, so let's start with the detailed explanation and step by step solution. So the system consists of two particles attached together, separated by finite fixed distance, and capable of rotating about an axis, possessing through the center of mass and normal to the plane containing the two particles constitute a rigid rotator. So let's start with this diagram first. So these are this is M1 and this is M2. Let R be the distance between the two particles. Okay. So let R1 is distance of atoms of masses M1, and R2 is distance of atom of mass M2 from the center of the gravity. The rotational energy are calculated by solving the Schrodinger wave equation. Here, rigid means the internuclear distance between the atoms of the molecule is constant. Okay. So therefore, let us start the Schrodinger wave equation first. The Schrodinger wave equation, we know this is the normal Schrodinger equation. I mean, d square psi divided by dx square plus 2m divided by h plus square E minus potential energy equal to 0. This is generally Schrodinger equation. So the Schrodinger wave equation in 3 dimensions in spherical coordinate is given by so we'd like to try this one is a Schrodinger spherical polar coordinate form. So r square partial derivative of psi divided by partial derivative of r plus 1 divided by r square sin theta dou by dou theta sin theta dou psi divided by dou theta plus 1 divided by r square sine square theta dou square psi divided by dou pi square plus 2m divided by h cross square e minus v wave function psi equal to 0. This is the equation number 1. So this is a spherical coordinate in three-dimensional form of Schrodinger wave equation. So remember here, this is the rigid rotator problem we are solving. We have to see that potential energy is 0. Okay, so then we need to use r equal to 1 here, and the mass m may be replaced by the momentum of inertia I. I'm going to replace the momentum of inertia I. Therefore, the Schrodinger wave equation for rigid rotator become as like this. Okay, here 1 right, it's going to vanish, and remaining term is 1 divided by sine theta, because r equal to 1, dou by dou theta sine theta dou psi divided by dou theta plus 1 divided by sine square theta dou square psi divided by dou pi square plus 2i divided by h cross square e wave function psi equal to 0. This is equation number 2. This equation consists of two variables. One is theta, right? One is theta, another one is the pi, which represented the precessional motion of the rotator, free axis, and the rotation of system respectively. So therefore, the solution of this equation of wave equation eigenfunction for rotator, this equation number 2 may be solved by the method of separation of variables. That means the wave function psi of theta comma pi must be represented like this. I'm going to write this big theta, okay, theta of theta, and pi of pi, okay, pi of pi, like this. This is equation number 3, where this theta of theta is a function of theta alone, and pi of pi is a function of pi alone. Now I'm going to substitute this wave function in equation number 2, first step. So let's see what happened here. So if you substitute in place of psi, the separation of variable function. Here pi is there. I'm going to write pi function here. Remaining theta is there here. I'm going to write theta here. Pi is constant. I'm going to write outside the bracket. So okay. Pi 1 divided by sine theta dou by dou theta into sine theta dou theta divided by dou theta plus here pi is there. I'm going to use pi here. Remaining theta I'm going to write outside this function. Theta divided by sine square theta partial derivative of pi divided by dou pi square plus 2i divided by h cross square e theta to pi equal to 0. This is equation number 3. Now I'm going to divide equation number 3 by function theta and pi. So why I am doing this step? We need to solve this equation like a left hand side should be one function, right hand side equals should be one function. We need to here see if you look at this function first term, here the pi is there, theta is there. I want an equation like a left hand side equation. I mean one side equation theta form, another side equation is pi form like this. So I need to find the solution like this. I mean we need to write, sorry, we need to separate these variables individually. Okay. So if you divided this function, final equation you'll get 1 divided by pi gets cancelled, theta is there, remaining theta, sine theta here, first term, remaining function all the same. Please no need to change here. So big theta divided by small theta plus here theta get cancelled, remaining term 1 divided by pi sine square theta partial derivative of pi divided by dou pi square plus theta and pi both are cancelled, remaining two term is 2ie divided by h cross square equal to 0. This is equation number 4. Then multiply this equation by sine square theta. Then you'll get this equation like this. Sine theta divided by theta dou by dou theta sine theta partial derivative of theta divided by small theta plus sine square get cancelled, 1 divided by only pi in the second term, cos square sine divided by dou pi square plus 2ie divided by h cross square sine square theta equal to 0. Okay, here if you look here, two terms are there in the form of in the function of theta. A third term is the pi function is there. So therefore we are going to write this equation like this: sine theta divided by theta dou by dou theta sine theta plus 2ie divided by h cross square sine square theta equal to 1 divided by pi dou square pi divided by dou pi square. So this is equation number 5. In this equation, right hand side is a function of theta alone, while left hand side is a function of pi alone. If this equation is to be satisfied, both sides must be equal to the same constant. Then I'm going to use the constant here, the m square. Sine theta divided by, it is already there, right? Equal to m square. This is equation number 6. And minus 1 divided by pi, partial derivative of pi divided by pi square equal to m square. This is equation number 7. So if you look at here, as I said, the both sides must be equal to the same constants. That's why I'm using here m square. Okay. The solution of this equation number 7. So I'd like to first solve this equation number 7. Next, we'll go discuss this equation number 6. So this solution, it should be the second order differential equation, right? So therefore, we need to write like this. See here, partial derivative of pi divided by partial derivative of pi square plus m square pi, right, equal to 0. So I'm going to write the solution of this equation, this partial differential equation solution. So this is our well-known solution. So many times we solve this equation. Therefore, the direct I'm going to write the solution. Pi, even if you try to solve this Schrodinger equation, you'll get the wave function psi is equal to the a e power I n pi, right? Similar solution we need to use here. So wave function here, wave function in terms of pi is there, right? So pi constant exponential I, and m is there, and function is pi. Okay. If you want detailed information about this solution, we'd like to discuss this solution later actually. So this solution we call the azimuthal wave function solution. So we'll get easily this after solving normal. If you take the normalization arbitrary constant of values, then we'll find the a constant value by using the normalization condition. So here the a is the after using normalization condition, constant a is 1 divided by root 2 pi. Okay. Here m is azimuthal. Okay. Here where m is the values 0, plus or minus 1, plus or minus 2, plus or minus 3, and so on, etc. Therefore, the final wave function solution pi equal to 1 divided by root of 2 pi e power I m. So this is our equation number 8. Okay. Now try to solve the other equation. Here I'm not going to give the any equation names like radial equation, azimuthal equation, and other solution. So generally I'm going to solve this. Later we'll discuss the names and other things. Equation number 6 is there, right? Equation number 6. This is our equation number 6. Right? So I'm going to okay, this is our equation number 6. Then multiply this equation number 6 by theta divided by sine square theta. We'll get the 1 divided by sine theta dou by dou theta into sine theta dou by dou theta plus 2ie divided by h cross square minus m square divided by sine square theta into theta equal to 0. After multiplying this equation, you will get this. So, this one. So here we need to define a new variable. So let us now define a new variable x such that x equal to cos theta. So from this sin theta we can write root of 1 minus x squared. Sin square theta plus cos square theta equal to 1, right? So use the equation simply, we'll get this equation. Then let us start with the partial derivative of theta divided by dou small theta equal to, I'm going to write this function like this. I mean this operator like this, dou by dou x, partial derivative x divided by dou theta. Now what is the differentiation of partial derivative of theta here? So try to substitute this value here. Minus sin theta, right? So therefore the minus sin theta dou theta divided by x. So this one, after derivating with respect to theta, I mean partial derivative of x divided by partial derivative of theta, you get minus sin theta. This information I am using here. Okay. So we have function dou by dou theta equal to minus sin theta dou by dou x, right? So multiply both sides into sine function here. What will get sin theta dou theta, the theta is there here, right? Big theta, I mean small theta equal to minus sine square theta, partial derivative of theta divided by partial derivative of x. So sine square theta equal to 1 minus cos square theta, right? Minus 1 minus x square, because x is defined by cos theta, partial derivative of theta divided by x. So we are going to use these functions in our equation. Let's try to solve the remaining the equations. First one, this one. Okay. I am using this equation. here sin theta dou theta divided by dou theta. We need to use here minus 1 minus x squared dou theta divided by dou x. 1 divided by sin theta dou by dou theta is there. So in place of 1 divided by sin theta, from this information, okay, from this information here, from this information, this we got right, 1 divided by sin theta dou by dou theta divided by dou theta equal to minus theta theta get cancelled. I mean sin theta get cancelled. Dou theta divided by dou x. This I got actually. So use these two terms here. In place of 1 divided by sin theta dou a by dou theta equal to, we'll get this one. So no need to use function here. That's why I didn't use initially function. Okay. And in place of sin theta dou theta divided by dou theta, so therefore the final equation after using these two terms, the final modification term we got d by dx into 1 minus x squared partial derivative of theta divided by partial derivative of x plus 2i e divided by h cross square, right? So I'm going to use this term, the beta here, minus m square divided by 1 minus x square into theta equal to 0. This is equation number 10. So we need to use this equation number 9, this one. Okay. This is equation number 10. So here beta I'm using the 2i in place, right? 2i divided by h plus. Remember this. So this is the final equation I got after putting a lot of new variables. So this equation, this solution equation is look like a Lagrangian equation. Lagrangian equation, and it has physical significance only for values of x between the limits -1 and +1. Since x is equal to cos theta with beta is equal to L into L plus 1, it is called associated legendary equation. So here I would like to write down original or mathematical legendary equation, I mean associated Lagrangian polynomial equation. So let's see here, divided by x, 1 minus x square. Similar function I am using here, but slight different is L into L plus 1 minus x m square 1 minus x into the theta equal to 0. So if you look these two equations, one is equation number 10. This is our original equation. Okay. This is our mathematical equation. If you compare here, in place of beta, in place of 2ie divided by h cross square, L into L plus 1 is there. L into L plus 1 is there. That's why I'm using here the beta. So the solution of this equation is, the associated Lagrangian function, we need to write like this: P L M of x equal to 1 minus x square whole power m divided by 2 dm PL of x divided by dx power m, where this P suffix L of x is a legendary polynomial of degree L. Lagrange polynomial of degree L. So the solution of this equation number 12 is theta equal to B PL M of x equal to B PL M. X we are considering the cos theta. That's why we are introduced the new variable in the solution, x is equal to cos. Okay. Now we got the all solutions. So try to write down the equation, eigenfunction of this equation. So for that we need to write the according to the orthogonal property of associated Lagrange polynomial So we have two equations, two conditions are there: integral -1 to +1 p k of x m p l of x m dx equal to 0 for k not equal to L case. Another case is integral -1 to +1. If not equal to 0, we'll get some other value. P L m of x dx equal to 2 divided by 2L plus 1 L plus m factorial divided by L minus m factorial for the case of k equal to L. Okay. use the equation numbers perfectly. This is equation number 13. This is equation number 14. So according to normalization condition, integral theta of ml theta of ml d theta equal to 1, right? Then use our equation here. B is there, b square minus 1 plus 1 plm of x plm of x dx equal to 1. So this is our condition. So b is there. So b, simply I am using this one for normalization condition. No need to confusion here. Okay, this is our function. Just I am simply using this function here, the normalization condition. Then I am trying to adopt this condition with our polynomial associative forms. So if not equal to 0, right? If not equal to 0 condition is there, then we try to use this one. 2 divided by 2l, k equal to l equal to 2 divided by 2l plus 1, k equal to l. If l plus m factorial divided by l minus m factorial. For the case of k equal to l condition, because here the two functions are same is there, right? That's why I'm using the second condition. Okay, so therefore we got the b square 2 divided by 2 l plus 1 l plus m divided by l minus m factorial, here also factorial is there, equal to 1, from equation number 14. Therefore I got b value also, b equal to root of 2l plus 1 divided by 2 l minus m factorial divided by l plus m factorial. We substitute this value in equation number 13. So equation number 13 is this one. So b pl, yeah, pl of x, right? We got the theta of theta equation. Theta of theta equal to root of 2l plus 1 divided by 2 l minus m factorial divided by l plus m factorial pl m of x. In place of x I'm using cos theta. That's it. So we got different type of equation here. This is one, and one more solution is pi solution. Where is our pi solution? Here, right? See this one, pi solution. So total wave function of our system we are using here, the wave function psi equal to theta of theta and pi of pi, right? That's why we solve the two solutions. So therefore our final solution is m l theta pi equal to root of 2l plus 1 in divided by 2 l minus m factorial divided by l plus m factorial PLM of cos theta, and azimuthal solution is 1 divided by root of 2 pi e power I m pi. This is our final eigenfunction of rigid rotator. Okay. Then we need to calculate eigenvalues. That is simple. Just compare the two Lagrangian equations. 2e divided by h cross square equal to L into L plus 1, right? I'll show you here. Yeah, here. So this is our equation, right? And here we got the comparison equation. Then we try to equal these two terms. That means 2ie divided by h cross square equal to L into L plus 1. Therefore, E equal to L into L plus 1 h cross square divided by 2i. This is eigenvalue equation. So we have eigenvalue energy value equation, eigenfunction. This is our eigenfunction of rigid rotator. This is our this equation is a final eigenfunction of our rigid rotator. So this is the final eigen values, energy values of the rigid rotator. Where the beta is here the constant. If you try to use this equation like this, B into L into L plus. This is what we are using generally in textbooks. So here the B equal to h cross square divided by 2i is called rotational constant. Rotational constant. Rotational constant. Substitute L equal to 0, 1, 2, 3 and so on, 2, 3 and so on. You will get the energy eigenvalues of the system